We learned how to find the empirical formula of a compound from either the percent composition or just some mass information about the different elements. How do we figure out what the actual molecular formula is? Well, the empirical formula multiplied by some number is what gives us the molecular formula. Sometimes they're the same, so that multiplier is just 1. Other times the molecular formula is 2 or 3 times the empirical formula. To figure out what the molecular formula is, we have to have the molar mass of the compound. Molar mass can be determined in many ways, but it involves experiment. And so when you're doing a homework problem, when you're doing an exam problem, we're not going to have you go off and do an experiment to find the molar mass. You have to be given the molar mass, because there's no other way for you to figure it out. So we'll give you the molar mass and either the empirical formula or the information to find the empirical formula. And then to find out how many times to multiply it, we're going to take the molar mass that's given to us and divide by the mass of the empirical formula. That tells us how many times to multiply the subscripts. This will always give you nice whole numbers unless you made some silly calculation error. So let's do an example. Compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? So we're looking for N. We want to find out how many times does the empirical formula go into the molecular formula. So to find N, we take the molar mass, which is given. That is the molar mass of the actual molecular formula. And then we're going to divide by the molar mass of the empirical formula. So the empirical formula is CH. So we have to calculate that. There's 1 carbon and 1 hydrogen. And so I think that's 13.018 grams per mole. Every mole of CH would weigh 13.018 grams. So I'm going to put that in the denominator. Pull out my calculator. 78.11 divided by 13.018. My calculator gives me 6 with 3 zeros before it gives me another digit. It's just going to come out to a number 0.0 whatever. So that is 6. That tells me that the molecular formula is 6 times bigger than the empirical formula. So we could think of that as taking that empirical formula and multiplying it by 6. We would never write it like that, but that kind of helps us understand, well, what am I doing with this 6? This 6 then is going to multiply all the subscripts. So that's going to be, start out right here, C6H6. Question?
So when you did the division, you resulted in 6.0001. That's 5 significates, right?
Well, yes. It's always going to round to a whole number.
Okay.
I was just showing you how close to a whole number it was.
I see, okay.
Yeah.
Got it.
Good question, though. Anybody else? Okay, let's talk about combustion analysis. This is a common technique for analyzing compounds that will burn. So we take a known mass of the compound, we burn it, we collect the products, and we weigh them. This works really well for organic compounds that contain carbon, hydrogen, and possibly oxygen. When a substance like this burns, all of the carbon combines with oxygen to form CO2. All the hydrogen in the compound combines with oxygen to form water, and then the mass of oxygen that was in the compound is a little trickier, but if it only contains carbon, hydrogen, and oxygen, and we find the mass of carbon, we find the mass of hydrogen, and we know what we started with, then we can find the mass of oxygen as the missing part, okay? So here's a picture of what an instrument might, kind of look like. So we have a furnace, and we've got a supply of oxygen because it won't burn without oxygen. So we weigh the sample, we stick it in here, we burn it. Oxygen's flowing through here, and the gases that are given off will go with the oxygen through a series of tubes. The first tube contains a substance that will absorb water. So you weigh the tube before the experiment. After you burn this, water gets trapped in here, and it will weigh more. So the difference in mass of this is the mass of water given off. And then the gases continue through here, through a CO2 absorber, which catches all the CO2. And you can find the mass of CO2 by weighing that. Any other substances that are produced will just go straight through. So if you're burning something that has nitrogen in it, you would need to do something else with that. But we're just going to talk about carbon, hydrogen, and oxygen. So here's a typical example. Upon combustion, a compound containing only carbon and hydrogen produce 1.60 grams of CO2 and 0.819 grams of water. Find the empirical formula for the compound. What do we need first? What was the first step in finding an empirical formula? The mass of the elements? We need the mass of each element, right? To find the empirical formula, we need the mass of carbon and the mass of hydrogen. They didn't give us that. They gave us the mass of CO2. So I'm going to make a little cheat sheet up here. So you start with masses. You convert the masses to moles, and then you make ratios. And then sometimes you need to multiply to get whole numbers. That's just kind of steps. That's not a path for dimensional analysis. Kind of looks like that, but I don't know. Well, we've got a mass of CO2, 1.60 grams of CO2. So the formula is giving us information about the amount of carbon in moles in 1 mole of that compound, right? 1 mole of CO2 has 1 mole of carbon in it. Can we find out how many moles of CO2 we have? Sure, we just need the molar mass, which is 12.01 plus 2 times 16 is 44.01. So I can convert this to moles of CO2 dividing by the mass, the molar mass of CO2. So grams of CO2 cancel out. I can find moles of carbon just by looking at the chemical formula. CO2, there's 1 C. So there's 1 mole of carbon for every 1 mole of CO2. Now I could convert the moles of carbon into grams of carbon. But when I get grams of carbon, what's the first thing I do? I convert it to moles of carbon. So maybe let's just stop here at moles of carbon. So 1.60 grams of CO2 divided by 44.01 times 1 over 1. And with all of these, we want to make sure we keep at least the minimum. Ultimately, the sig figs go away, but you'll get the wrong formula if you don't use enough. Yeah, this will be moles of carbon. Because to get the formula, we need the moles of each element and then find the whole number ratio. So we can do a similar process to find the moles of water. I'm sorry, the moles of hydrogen from the water. 0.819 grams of H2O. So we'll convert that to moles of water using the molar mass of water. And then we'll convert to moles of hydrogen. How many moles of hydrogen are in 1 mole of H2O? 2. There's 2 moles of hydrogen atoms in 1 mole of H2O. And then those units. 0.819 divided by 18.016 times 2. So that's moles of hydrogen. How do we get a whole number ratio out of this mess? Divide by the smallest, right? So 0.09 is bigger than 0.03. So I'm going to divide by the 0.036355. And that gives me 2.500. Is that a nice whole number? No. This other one, we're dividing by itself, and so that one's going to be 1. Something is always going to come out to be exactly 1 because you're dividing it by itself. How do I make 2.5 into a whole number? Multiply by 2. So if I take 2.5 times 2, I'm going to get 5.0 and stuff. This is definitely within 0.2 of a whole number, so I can keep that as a whole number. If I multiply that one by 2, I have to multiply this one by 2. And so this one ends up being 2. So the empirical formula is C2H5. Any questions? We'll do one more. This one has carbon, hydrogen, and oxygen. This one's a challenge to fit all the work on this one screen. So on your paper, you might need the whole page. So upon combustion, 0.8009 gram sample of a compound containing carbon, hydrogen, and oxygen produced 1.6004 grams of CO2, 0.6551 grams of water. Find the empirical formula. There is also oxygen in the compound, so we can't just use these numbers. We have to find amount of carbon, amount of hydrogen, and the amount of oxygen. So we're going to do the carbon and the hydrogen first. So same process as in the previous example. So here's a mass of CO2. We're going to convert that to moles. That's an excellent question. So this has carbon and oxygen. Should we find the oxygen in the compound from this oxygen or from the other oxygen? The answer is no. The oxygen in here could possibly be from the compound, but it's more likely to be from the vast quantities of oxygen gas that we're shooting into the furnace. So this oxygen amount is not useful. But we can find the mass of carbon, we can find the mass of hydrogen, and then we know the total mass. Okay, so we find the mass of oxygen by difference at the end. Excellent question. So moles of CO2, the CO2 gives us information about carbon, and so we'll convert this to moles of carbon. And this is where I'm thinking ahead because I've done this so many times and I need to save space. Do we need moles of carbon to find the empirical formula?
Yes.
Yeah, we do. So I want this number in here, so I'm going to do the calculation here and write that down. Bless you. 0.03636, see, 245. 1, 2, 3, 4, 5. I'm going to throw caution to the wind and only use the minimum number of sig figs here. That would be moles of carbon. So I need that, but in order to find the oxygen, I'm going to need the mass of carbon as well. So I'm going to go ahead and just add that calculation in here. I'm going to multiply by the molar mass of carbon to get the mass of it. So that number times 12.01. And that's going to be 0.43674 grams of carbon. Now we'll take the water, 0.6551 grams of water. We're going to get the amount of hydrogen from this. So we're going to convert to moles of water using the molar mass of water. And then we're going to convert to moles of hydrogen. Whoops. And that conversion comes from the formula, H2O, so there's 2 moles of hydrogen in every 1 mole of oxygen. I'm sorry, 1 mole of water. So that's my moles of hydrogen. And I'm also going to need the mass because I have to find out how much oxygen was in that compound. So that's grams of hydrogen. And this is carbon up there. This compound has 3 elements in it: carbon, hydrogen, and oxygen. We need the moles of each. So we've got moles of carbon, we've got moles of hydrogen. We haven't found the oxygen yet. So we're going to find the mass of oxygen by difference. So we've got the total compound mass, 0.8009 grams. And then we're going to subtract the mass of the carbon, minus 0.43674 grams. And we're going to subtract the mass of the hydrogen, .8009 minus 0.43674 minus 0.07331. And my calculator is giving me 0.29085. and the sig figs would end right there. That is grams of oxygen. Any questions? Yeah, perfect face for this one. Lots of little steps. I need moles of each element so I can get ratios. So here I just found the grams of oxygen. I have to convert this to moles of oxygen. So 1 mole of oxygen from 16 grams. So I take the number in my calculator, divide by 16, 0.018 moles of oxygen. So moles of oxygen, moles of hydrogen, moles of carbon. I need to find the ratios. So I divide all of the moles by the smallest one. The smallest one is 0.0181, right? So this one I'm dividing by itself, so that's going to equal 1. Up here, I'm going to divide this one by 0.01818. And that came out to 4. That's pretty. And then this one, 0.01818, 0.036364 divided by 0.01818. And that comes out to 2 with a bunch of zeros. Close enough to round to 2. So I've got a 2, I've got a 4, and I have a 1. So those are the subscripts. Make sure you get them with the right element. Carbon was first, carbon 2, hydrogen 4, oxygen 1, but I don't write the 1. Any questions? Yeah.
So I guess my only fear is remembering to do all this in order properly. Does it all make sense when you lay it out like that?
That is the trick, is just remembering what to do. So what I find works for me the best is if I really understand what it is that I'm trying to find, if I really understand that the empirical formula is the ratio of amounts of particles, so the moles of each element, and I'm trying to get whole number ratios of the moles of each element. Then on a test, when I've forgotten this list that I made myself memorize of what to do, I can say, well, I need the moles of each element. And then hopefully I can figure out how to do that, right? And so that's problem solving and critical thinking. One of the things that really messes with students in Chem 1A is this is not like high school or elementary school where they taught you how to do the problems that are going to be on the test. Like, okay, let's learn how to calculate the area of a circle. And so everybody learns how to do it, and you remember that, and great. You give me this stuff, I can do this one problem. I'm a trained monkey, right? But if I give you the area of a circle and ask you to find the radius, you go, we didn't go over that, right? There are a gazillion variations of all these problems. They're not always going to be the same as the ones I give examples for. Life doesn't always give you what you were trained or taught how to do, so you have to be able to think and come up with a way to figure out an answer to the problem, okay? And that's sometimes kind of painful to try to be learning that, but that's what you need to do well in this class. So please ask questions. Anybody else? Yeah.
Like I have different ways to do it, but I mean there is a savings use.
There are other ways that you can go about this. Yes. I would really like you to be able to write it down so that, like, if it's on an exam, that I can follow what you're doing. It's really important to be able to write down what you're doing so that someone else who understands the problem can follow it. Okay? That way, on a problem with show your work, if you get the actual answer wrong, but your work is really good, I can give you most of the credit for the problem. If you don't show me any work and your answer is wrong, then you get a big fat 0. Any other questions?